Hello everyone, welcome, good morning, good afternoon, good evening. In this video I want to talk to you about what we call the fundamental theorem of calculus. Now in the prior two videos what we have done is introduce the idea of integration, of integrals by starting with the conversation of area under a curve. That's how we have initiated, or how we've motivated that conversation to introduce that concept. And we're going to take that conversation a little bit further, and we're going to discuss the fundamental theorem of calculus. Now, just a quick review here of what we did in the prior two videos. If we had some function, let's say it looks like this, and we were wanting to estimate the area under this curve, let's say from A to B. Those were kind of the generic symbols that we used. We wanted to find the area under this curve, and what we would do is, let's say if we used left endpoints, we would come up, we would draw a rectangle, and then from this endpoint, from this point to this point over that interval, we would come up, draw from a left endpoint, and then let's say from this number to this number, we would come up, we would draw a left endpoint, something along those lines, right? We did those gory details in the prior two videos, but that was the general concept. And what we did in those prior two videos is we said that the area under the curve would be approximately the sum of all of those rectangles. So we had the width of the rectangle, the delta x, and then we had the height of the rectangle, the y value. And again, we discussed a little bit more in a general manner. If this was the first rectangle, we have its height at the function value, right? If this was the second rectangle, we had its height at the function value. So we used subscripts. We said for the ith rectangle, and we would sum up the area of all n rectangles. Something along those lines. And then we said that the area would be exactly equal to the limit as we squeeze infinitely many rectangles under that curve. I'm just going to rewrite the order of our heights of our rectangles and our widths. And one of the things we discussed that as we squeeze more and more rectangles into this space, the delta x between the endpoints is going to get smaller. So, two ways to describe this limit: the delta x's go to 0 or the n goes to infinity. We called this the Riemann sum, and we said that symbolically we're going to represent as an integral. We're going to integrate the equation of that function and over the limits of integration from a to b. So in that prior two sections, right, this was the development that we used here. Now, evaluating this limit of the Riemann sum was very difficult. It was very lengthy and tedious, and so we want some shortcuts, if you will. So this is kind of like when we did equations of tangent lines. Remember what we did with equations of tangent lines is we had a graph of some function, and we said, what's the slope of the tangent between, let's say, this point at this point, right? We wanted the slope of that tangent line. What we did initially is we found the slope of the secant line between these 2 points, and we let's say this point move closer and closer and closer, and we got more of a average rate of change became an instantaneous rate of change. So we said something like this, f of x plus h minus f of x all over h. And if we called this x and we called this distance h here. The only reason I'm bringing all of this up is in order to find the instantaneous rate of change, the slope of the tangent, we started off with an average, and then we took a limit as h went to 0. And when we first did these problems, they were lengthy and they were tedious. And we ended up discussing shortcuts, if you will. We discussed, the quotient rule, the power rule, the chain rule, the product rule. So, and in a very analogous manner, in 5.1 and 5.2, the first two sections that we've discussed in this chapter of integration, we have motivated the conversation with area under the curve. We started off approximating that area, and then we used the limit process to find an exact measurement. So I just want to kind of revisit both of these approaches here, because the limit tool is what's really powerful here. The limit tool is allowing us to develop an approximation and make it an exact measurement. Now, in regards to an integral, how we officially defined the integral was this guy. We looked at the limit of the Riemann sum. With a derivative, we did the limit of we called this the difference quotient, right? So for an integral, this is the limit of the Riemann sum. And again, like we talked about in the prior video, what we're going to do symbolically is this Greek capital letter sigma we're going to represent with the integral, right? And then the height of every rectangle, at the left endpoint, let's say, we're just writing as f of x, the height of the function, right? And then the delta x we're writing as a dx symbolically. So in this section, what we want to do is take a look at this idea of this integral, and we want to develop some shortcuts, if you will. So before we just write out the fundamental theorem, what I want to do is an exploration here. There's a really cool instructor's resource manual that comes along with Stewart's textbook, and it has something similar to this, and I developed it, augmented it, edited it for something that I like to use in my classes. So let's work through this together in the video, and we're going to end up doing is discovering what the fundamental theorem of calculus really says. And then we will write it in a very general form, as you typically see it in a calculus textbook. So let's take an exploration here. So the first thing we're doing, I'm reminding us at the top here, is recall that we can use the notation, the integral of f of t dt from a to b, to denote the area under the curve f of t between t equals a and t equals b. So that's just what we discussed, right? If we're finding the area under the curve y equals 4, and this is the horizontal line y equals 4, I could use approximating rectangles, but we're going to discuss how to do this exactly. This is our exploration. Now, in order for us to evaluate this integral and not have to use Riemann sums, I'm picking geometry that's pretty straightforward and easy to calculate. So, in other words, if I'm looking at the function f of t equals 4, the horizontal line y equals 4, and I want to evaluate the integral of 4 from 0 to 2. So we're interpreting this as the area of the shaded region, the area under the curve y equals 4. And let's first look from 0 to 2. And I want to use geometry. So let's pretend this is the number 2. So if I'm going from 0 to 2 here, what's the area of this geometry, of this rectangle? Well, I have, let's say width times height, if you will. So the area of this guy is, let's say, width times height. And for this particular example, the width of the rectangle is 2, and the height of the rectangle is 4. So in this case, that would be 8 as my area. I'm going to leave a little space here because I want to come back and add some extra stuff in just a second. So now let's find the area under the curve from 0 to 3. So I'm going to come over to my graph, and I'm going to erase the 2, and I'm going to pretend this is now from 0 to 3. So in a very similar manner, I'm going to have width times height, because this is the geometry of a rectangle. So my width is 3, right? So I have 3 as my width, and then I have the height of 4. So I get 12 in that case. Now the next one is to integrate from 0 to 4. So let's say I now erase this guy and call him 4. So I have width times height for that integral. And so the width, again, is this distance of 4. And then the height is also a height of 4. We get 16 in that case. Now what I want to do on the next part here is let's abstract. So we have a pattern of things. And instead of going from 0 to 2 or 0 to 3 or 0 to 4, I want to go from 0 to x. Right? So in other words, what I want to do here is I'm going to erase, and I want my t-axis to go from 0 out to x. That's what we're looking at. Now, I don't want to have to scroll down here, so I'm going to scribble up here what we're looking at. Let me write it in green. So if I'm going the integral from 0 to x, right, I'm looking at, width times height. So what is the width of my rectangle? Well, it is, this length for the number x. So that is the width of my rectangle. And then what's the height of my rectangle? Well, for this particular equation, that is going to be 4. So we have just created an expression, if you will, for the area under this curve for any x that I choose. So if this is from 0 to 2, we get 4 times 2, which is 8, and that's what we see here, 8 that we got. If we go from 0 to 3, we get 4 times 3, which is 12. We can see that's what we got here. And again, if this is 0 to 4, we see that we get 4 times 4, which is 16. And from 0 to x, we're going to get 4 times x, whatever that x is going to be. So we found, basically, I'm going to rewrite all of this work, 0 to x, 4 dt. We said that that was 4, right, times the width. Or, let me rewrite this. I just want to have this as a reference, even though we wrote it already. Width times height. So we said that was x times 4, and I'll just write that as 4x. So we just created a general formula to calculate the area under this curve from 0 to x, and that was 4x. Okay, so we have evaluated an integral without actually knowing the quote-unquote shortcut. Some of you have maybe already seen the shortcut, but we're developing this idea to get to the fundamental theorem. So we evaluated this integral, interpreted it in terms of area, and we used geometry. So I picked a specific example of y equals 4 so that the geometry would be doable. Right? We'd be able to evaluate that. Now we're going to look at a different example. So instead of picking the curve y equals 4, we're going to pick the curve y equals 2t that we're going to find the area. Now again, I picked this equation because the geometry will be relatively simple. We have a triangle that we're going to be finding the area of. So again, we're going to use geometry. No need to use approximating rectangles and a Riemann sum. We're going to evaluate this integral with geometry of that area. So here's the curve y equals 2t. And let me switch back to blue. So we have y equals 2t. So what is the area of any triangle? The area of any triangle is 1/2, let's say, base times height. So if I'm thinking of the bottom dimension as the base, right? Thinking of the side dimension as the height, right? So from 0 to 2, so again, I'm going to pretend from 0 to 2, that's my limits of integration. So I have 1/2, the base is 2, and what is the height? So if the x value, right, if my domain input, if you will, is 2, what's the y value? Well, it's going to be 2 times 2, which is 4 in that particular case. Right? So the height of that rectangle is 4. Now if I crunch that number out, what do I get? 4 is that result. So let's do the next example. I'm going to integrate from 0 to 4. So I'm finding the area under the curve from 0 to 4. So I'm going to come back over here and let me erase that stuff. And we're going from 0 to 4 on my independent axis. Independent axis, going from 0 to 4. So again, this is a triangle. I'm going to have 1/2 base times height. And we have 1/2, right? What's the base? Well, the base is from 0 to 4. And what is the height? So again, what is the height here? So I'm going to take 4, plug it into this equation. 2 times 4 is 8. So I'm going to get what there? I'm going to get 16 as the end result. Now let's take a look at the next one. So the next one, we would have, again, a triangle. 1/2 base times height. We're going to get 1/2. So, oops, I'm going from 0 to 5. So let me label my axis, my values here, going from 0 to 5. And then the height of this rectangle, height of this triangle is 2 times 5, which would be 10. So my base is 5, my height is 10, and I get 25 as the area. Now what I'm going to do in letter D is what we did in letter D in the prior problem. I scroll down, and then I'm going to scroll back up just so I can see my graph here. So I want to use part A through C as a guide. We want to compute the area from 0 to any number x. So I don't want this number here in my domain to be anything in particular. I want it to be some arbitrary number x. We're generalizing to x. Right now, give myself a little bit of writing room. So I know that that integral is going to be 1/2 base times height in terms of the area. Let me squeeze back up. Let's see if we could peek here. So what's the base of my rectangle? Well, the base is going to be that value of x. So I have 1/2 times x. And then what's the height of that rectangle? Well, just like we did before, I'm going to take this number and plug it into the equation. Right? So if I take this number and plug it into the equation, my y value here, I didn't erase that guy, is going to be twice the input, 2 times x. That's my y value. So again, when this was 5, I got 2 times 5, which was 10. When this is any number x, I'm going to get 2 times that input, which is 2x. So the height of that rectangle is 2 times x. And when we multiply all of this out, we end up getting x squared. Now, if we kind of go back and check our answer, right, if the upper limit of my integral is x, then I'm just squaring that as my area. When the upper limit was 5, 5 squared is 25. We can see that's our answer. When the upper limit was 4, 4 squared was 16. So we can see that that's matching the pattern that we saw before. So again, just to summarize this, we have created an area function for this particular integral, and it's x squared. So I'm just calling this b of x to represent the area under the line y equals 2t from 0 to x. And on the prior page, I called this a of x, just so we can distinguish between the two. So to just summarize, when we had f of t equals 4, a of x was 4x. And I have a typo here. When f of t was 2t, our b of x was x squared. So here's just a summary of the two prior area equations that we got. And what I want to point out to ourselves, right, let's differentiate each of those area functions. So for the first equation, y equals 4, we evaluated an integral. And the integral of 4 became 4x. So this is the output of the integration. And when we differentiate that output, derivative of 4x is 4. And notice something unique, right? This output that we got here is the original function that we started with. Now let's look at the next example. We're going to notice the same thing. So when I integrated 2t, the output of the integral was x squared. And when I differentiate x squared, I get 2x. So what I can notice in that case is that takes me right back where I started. All right, so what we're noticing in essence is that the integral does its thing and produces an output. And then when I differentiate that, it undoes what the integral does. Right? When I took y equals 2t and I integrated, it did its thing and got x squared. And then when I differentiated, it did its thing and got 2x. And so the derivative is undoing the integral. Right? So let's say here the derivative undoes the integral. And this is what the fundamental theorem of calculus really tells me in words, is that the derivative undoes the integral. So, in an algebra class, when two things undid each other, we call those inverses. Right? So like the square function and the square root function undo each other. We call those inverse functions. The integral is not a function. The derivative isn't a function. They're both operations. So we could say the derivative and the integral are inverse operations. Derivative and the integral are inverse operations. And this is the fundamental theorem of calculus, and we're going to write it out formally in just a second. So just to hammer home this idea, the next problem I have on this exploration is, Let's suppose, whoa, where are you going? Let's suppose we want to find the area under a curve, and the curve is really ugly looking, right? So we have this really nasty integral here, 0.2t sine of cosine of sine t. So t, we're integrating from 0 to x. So we have our t-axis, and we're going from 0 out to x. And then here's the graph of that nasty function. And I hate to call that function nasty. I don't want to hurt their feelings. So it's really a beautiful function. We have this beautiful function. We're finding the area under. And we're going from 0 to x on my input. I want to calculate the area under that curve. I want to evaluate this integral. So I don't really want to evaluate that integral. What we just learned is the derivative and the integral undo each other. So in other words, if I'm finding right down here, I'm jumping ahead of myself. Right? Down here, what I want to do is find the derivative. So don't worry about trying to find a formula for the area. That's not the point here. But using this amazing fact we just discovered, let's fill in the blank. So what would the derivative of that integral be? So the derivative of that integral of, I don't want to have to rewrite all of this beautiful stuff. So I'm just going to say squiggly dt. So what we just learned is that the derivative undoes the integral, right? Whatever the integral does, the derivative comes back and undoes that. So in essence, the derivative and the integral cancel each other out. Derivative and the integral cancel each other out, if you will, and we just end up with squiggly. So in this case, come on, in this case, the squiggly would be 0.2x sine of cosine of sine of x. And there's our answer. Okay, now in this section, we're not really going to be looking at beautiful functions like that in particular. What we're going to focus on in this section is just really the mechanics of what the fundamental theorem of calculus says. And we will get into some really cool applications a couple videos from now, but that's not the focus here. The focus here is, what is the fundamental theorem of calculus and what does it really say? Right? How do we use it in practice? Remember a couple minutes ago I said we want a shortcut for evaluating integrals. I don't want to have to do the limit of the Riemann sums. So this shows us what the shortcut of the integral is going to be. The fundamental theorem tells us what that's going to be. Now I want to come back in a second here. I just want to point out to you, what our shortcut is. When we integrated 4, we got 4x. And when we integrated 2t, we got t squared. So what we really want to do, we're evaluating an integral. We want to have a shortcut to figure out how we're going to go from here to here. How do we go in that direction? How do we find that antiderivative? And this fundamental theorem of calculus tells me exactly how to do that. And it's what we're going to call an antiderivative, really. That's the language we're going to use here. So here's the most general way we can write what we just observed. And then, man, this is weird. Sometimes Microsoft Word does this weird stuff for me, right? This is supposed to say g of x, right? So g of x equals that integral. And then what's the derivative of that integral, right? What is the derivative of that integral? So the derivative of that integral, these cancel out, and I'm going to get just f of x. I'm going to get the integrand of the integral as a function of x. So here's what this is really saying to me. This says that when I evaluate an integral, we're going to get some function that we call g of x. And we know that the derivative of that function is the original integrand. It's just what we said. The derivative of that function is the original integrand. So this is going backwards, right, from what we did when we took derivatives. We're taking an antiderivative. So I'm going to really call this an antiderivative. Okay, so it's undoing the derivative. So the derivative and the integral undo each other. So the integral does a thing, finds the antiderivative, then the derivative comes back and undoes that work. So, and real quick before we do some more examples, just to see that in action, right? Here's the antiderivative. So the integral of 4 is 4x. This is the antiderivative, right? Why is this the antiderivative? Because if I take the derivative of this expression, I get right back where I started. Right? Ditto here, I'm integrating 2t. Right? What's the antiderivative of 2t? It's x squared. Why? Because when I differentiate x squared, I get right back where I started. So we actually, a couple videos ago, we had a conversation about antiderivatives. We just didn't really see the application in regards to an integral. So now we're tacking on this conversation of an integral. That an integral is producing a function, right? It's performing an operation. And the output of that integral is an antiderivative. So in a section like this, there's really two things that we're doing with this fundamental theorem. The first thing we're doing with the fundamental theorem is connecting to the idea that the result of an integral is an antiderivative. What we sometimes call part 2, I'm going to call this part 2, right? The Stewart textbook says part 2 of the fundamental theorem. I'm going to get lazy and say fundamental theorem here. Part 2 of the fundamental theorem basically says, look, what we're basically going to be doing is finding area under a curve, if you will, right? Visually, if I'm finding area under a curve, something like that, right? From A to B, let's say. So we're finding the area under the curve here. So this is a numerical measurement. Their area is 4 or 12. So this integral is really representing a numerical value. So how do we find that value? So we're going to take this function f of x and we're going to find its antiderivative. So usually in a second part of the fundamental theorem, instead of writing g of x, we're going to write this as cap f. And we're denoting that cap f is the antiderivative. Right? Cap f is the antiderivative. Okay, so the derivative of f is little f. Right? So cap f is the antiderivative. And notationally, we're going to say we evaluate from x equals a to x equals b. So fundamental theorem part 2 says we're going to find the antiderivative of our integrand. Here's our antiderivative. And then we're going to evaluate from a to b. And what that really means in this theorem is we're going to plug in the upper limit and then we're going to subtract with the lower limit plugged in. And that is going to calculate the area for me as a quote-unquote shortcut. So let's see this in action. And what I want to do is I want to come back to those first two examples that we had. So in the first two examples that we had, we were evaluating the integral of 4. I'm going to just switch back to the x variable. Right? And one of the examples we did was 0 to, 0 to 2 was the first one that we did. Right? Now if we scroll back up, we found out that that answer was 8. Number 1, part A, the answer was 8 from 0 to 2 under that curve y equals 4. So we now have our fundamental theorem as a shortcut. So the fundamental theorem says I'm going to take the graph y equals 4. I'm going to take the function y equals 4. I'm going to take its antiderivative, right? So again, we discussed this in a little more detail back in the 4.9 video, right? But it's saying what do I take the derivative of to get 4? And that was the function 4x. If I take the derivative of 4x, I get back to 4. So my antiderivative of 4 is 4x. And I'm going to evaluate from 0 to 2. So the fundamental theorem says I'm going to take my upper limit and plug it into the function. And I'm going to subtract with my lower limit plugged in. And we can see we would get 8 minus 0, which is 8. So in our exploration, we use geometry to come up with the value of 8. Now we're using our shortcut, our fundamental theorem of algebra, connecting to the integral produces an antiderivative. Let's do the second example, number 2, part A. I believe it was the integral of 2x dx. In fact, you know what? Let me just switch the variable here just to show you it actually doesn't really matter the variable here. So we had 2t dt for that integral. We did integral of 2t dt, and the first part was 0 to 2. So again, the fundamental theorem says I'm going to take the antiderivative of this expression. So what do I take the derivative of to get 2t? I took the derivative of t squared. And again, we already knew this from our first exploration. Right? And then I'm going to evaluate as t goes from 0 to 2, right? My upper and lower limits here. So then the fundamental theorem says plug in the upper limit. So I'm going to have 2 squared. And I'm going to then plug in the lower limit. I'm going to subtract those. And I get 4 in this case, which was this answer we got from number 2, part A. So again, fundamental theorem, quick summary, really says 2 things to me. The first thing it says is that the output of the integral is an antiderivative. And then I'm going to take my limits of integration and I'm going to plug in upper limit minus lower limit, right? That's part 2. So let's do a bunch of examples here to get some more practice with this. So in this first example here that we're going to do, let's say we want to evaluate the integral 4 minus x squared dx, and let's say x goes from 0 to 2. So again, I'm going to focus on the mechanics of the fundamental theorem, which again is our shortcut for how to evaluate an integral. So what I want to do first is find the antiderivative of this expression. And again, in our prior video for 4.9, we practiced antiderivatives. So again, what did I take the derivative of to get 4? That was 4x. And then what did I take the derivative of to get x squared? We used the power rule that we talked about. So I'm going to add 1 to the power and multiply by its reciprocal. And again, as a quick refresher, why is this the antiderivative? I should be able to take the derivative of this and get back where I started. If I take the derivative of 1/3 x cubed, right, I pull the constant off, derivative of x cubed is 3x squared. We can see that those cancel off and I get just x squared as the output. Right, so there is my antiderivative. And then what I want to do with that antiderivative is evaluate from 0 to 2. So the fundamental theorem, part 2, says plug in the upper limit. I'm going to have 4 times 2 minus 1/3 2 cubed. And I'm going to put brackets around this, right, because there's the upper limit, and I'm going to plug in the lower limit. Excuse me, so if I plug 0 in, I'm going to get 4 times 0, which is 0. Then if I plug 0 in here, I get 0 cubed, which is 0. So in this particular example, plugging 0 in gives me 0 everywhere. So here is the value of my integral. So for this particular example, that turns out to be 8 minus 2 cubed is 8/3. So let's see, if I get a common denominator, this is over 1, multiply the bottom by 3, multiply the top by 3, get 24 minus 8, so I get 16/3 as the value of that integral. All right, so I want to take a look at this graphically for a moment. And actually, I don't really need my graphing calculator just yet. Remember that visually, we can interpret this integral here as area under the curve, right? So if I quick sketch, come over here and scribble, this is the parabola x squared. Negative x squared flips it upside down, reflects it over the x-axis, and then I add 4, so it shifts the parabola up 4 units. So here's negative x squared plus 4, something like that. There's my parabola, quick rough sketch. And then from 0 to 2, so if x equals 0, that's here. If x equals 2, that's actually the x-intercept. 4 minus 2 squared is 0, and there's my x-intercept. So evaluating this integral is really finding, what color do I want to use now? Let's use gray. Right? We're really finding the area under that curve. And we have found through our fundamental theorem of calculus, our shortcut for evaluating integrals, that that area is 16/3. All right, so for this example, I want to discuss a couple different ways we can check that answer by using technology. So I'm bringing up Desmos here, and what I'm going to do is type out f of x equals 4 minus x squared. All right, I like to visualize my graph. So there's the graph that I'm evaluating the integral of, and I can see, here's my x-intercept, and here's x equals 0, giving me that point there. And then what I want to do is integrate that function from 0 to 2. So on Desmos, I'm just going to start to type integral, start typing integral, and it's going to come up with the integral as our type 3. Or I could click the little keyboard, and we can see under, I believe it's under functions. Where is it at? Is it under miscellaneous? There's my integral symbol. So I could just click my keyboard and get it there as well. All right, so close that. Close that. So I want to integrate from 0. I'm going to click here, 2, and I'm integrating f of x. dx. And it's telling me what we found already. Here is 16/3 as my answer. 5.33333333, right? 16/3. All right, now let's suppose you have a tool like a Texas Instrument graphing calculator, and I've mentioned in the past the TI Inspire can do symbolic manipulation. So literally in the TI Inspire, you could symbolically write out this expression and it'll find it for you. I don't have a TI Inspire on my computer, so I'm going to use the TI-84 here. And a couple different ways to do this. I'm going to do it probably the simplest way. I'm going to hit the math key. And once I hit the math key, I can see down here is the function integrator. So I'm going to punch number 9, and it's going to bring up the same thing that we have been dealing with, right? The symbolic form of the integral. So I'm going to type 0, and then I hit the up arrow, and I punch 2, and I hit the right arrow, and I type in my equation. And then I have to tell the calculator that the independent variable is x, so I hit my x key. And I want to hit enter. It's going to give me 5.33333, which we got the last time. The kind of cool thing about a TI is I can hit math, and then I can choose the first option, fraction, and it usually can give me the fractional form of that answer. So let's do a couple more examples here to just get a little more practice with our shortcut, the fundamental theorem of calculus we're going to use to evaluate integrals. So let's say we want to evaluate the integral cosine of, I'm going to try to pick different variables each time we do this. Actually, you know what? The cool thing to do with trig functions, we can use theta as our variable. So let's say we're doing the cosine of theta d theta, and theta is going from 0 to pi. So again, the variable in there doesn't really matter. The fundamental theorem says we're going to take the antiderivative of this function. So what is the antiderivative of cosine? It is sine of theta. And then we're going to evaluate from 0 to pi. So I'm going to plug pi in. I'm going to get sine of pi. And then I'm going to subtract with 0 plugged in. And it's sine of 0. So sine of pi is actually 0, sine of 0 is actually 0, and we're getting the integral's value to be 0. All right, now how is that possible? If the integral is area under the curve, how on earth am I getting a 0 area? Now if I again visualize this, let's think about the sine curve. Think about the cosine curve. We are integrating the cosine curve here. The cosine curve looks roughly something like this. From 0 to 2 pi is its period. So 0 to pi takes me here. I did not do a very good job drawing this without gridded graph paper, but we can see from 0 to pi, because this function's periodic, right? From 0 to pi over 2, we're finding the area that's here. And then I'm going to switch colors. From pi over 2 to pi, we are finding this area here. And remember what we talked about in 5.1 and 5.2, right, the prior couple sections, that we can have positive area and negative area. So any area that lives above the x-axis is positive area, and any area that lives below the x-axis is negative area. Due to the symmetry of this periodic trig function, right, These are supposed to be equal measures if I drew them very carefully. So whatever value I'm getting here, this is subtracting itself out, and I'm getting 0. So this makes sense now that we have visualized the integral in terms of an area value. And we could, if we wanted to, we could evaluate from 0 to pi over 2 to just find out what this numerical value really was. And that wouldn't be hard to do if we wanted to. Right? So I'm going to do that real quick. Right? If I'm changing this to pi over 2, the antiderivative is still the same. This just changes to pi over 2. Right? So the integral from 0 to pi over 2 of cosine theta d theta is just going to be sine of pi over 2 minus sine of 0. Now, look on a unit circle, or maybe I've memorized those values. Sine of pi over 2 is 1, sine of 0 is 0. So the area of that green shaded region is just 1. So the area of the red shaded region is -1. And when I add those two areas together, we're getting an area of 0. All right, in the next example, let's say I'm looking at the integral of e to the x plus the x to the e, let's say. And we're going from 0 to 1. All right, so again, fundamental theorem says take the antiderivative of this expression. So if I'm taking the antiderivative of e to the x, that is e to the x, because the derivative of e to the x is e to the x. If I take the antiderivative, if I take the antiderivative of x to a power, remember e is just a number. Right? E is 2.718 something something something. So this is x to a number. So its antiderivative is to add 1 to the number and then divide by that number, or multiply by its reciprocal. And again, if I take the derivative, why did I write a base of e? I apologize. The base is the variable x here. I have x to the power of e plus 1 over e plus 1, and x is going from 0 to 1. So I'm going to plug in the upper limit. I'm going to get e to the 1 plus 1 over e plus 1, 1 to the power of e plus 1. So I'm plugging 1 into this x value. I'm plugging 1 into this x value. And again, I like to use brackets just to show that now we're plugging in the lower limit. So I get e to the 0 plus, get 1 over e plus 1, 0 to the e plus 1. So if I simplify this a little bit, not a whole lot of simplification I could do, but there's a little. E to the 0 is 1, and then 0 to whatever power is 0. So I have e plus, I'm going to just write this as, oh yeah, I plugged 1 in here. I forgot to mention that simplifies. 1 to any power is just 1. And then we minus, so e to the 0 is 1. So technically there is our final answer. We could go crazy and get a common denominator between all of this stuff. Probably if you look in the solutions manual of a textbook, you would see that written as one fraction with a common denominator. I won't bother to go into that work because I want to keep focused on what the fundamental theorem of calculus says. So what I want to do for the next couple examples is focus more specifically on the antiderivative, right? Doing the integration instead of the limits of integration. Prior examples we've looked at finding an antiderivative and then plugging in upper limit minus lower limit. I want to focus a little more on some of the integrals you might see in this section, where the antiderivative isn't so obvious. So let's say I look at 2 plus x minus 3x squared all over x. Now when I see a fraction like this is not an obvious antiderivative. And just to point out to you some things that are not true. Some common mistakes is that some students would integrate the top. Why do I keep doing that? Some students would integrate the numerator, if you will, and then integrate the denominator. And that is not true. Okay? The integral of f over g is not the integral of f over the integral of g. So before I evaluate this integral in terms of an antiderivative, then what I would need to do is a little bit of algebra cleanup here. let's say we had limits of integration on this guy from 0 to 1. So what I would want to do first is split this fraction up over the denominator. Now this is completely legal algebraically, right? When I think about these three fractions that I just wrote have a common denominator, I could combine these three fractions with the common denominator of x, and then I'm just adding the numerators. So this step that we took here algebraically was legal. We haven't broken any algebra rules, right? And then what I'm going to think about here is I'm going to integrate 2 over x, and then this is just the integral of 1. And then we have, let me do it this way, right? We have minus 3x. And technically all of these integrals are from 0 to 1 here. So, then I pull the 2 out and I get 1 over x dx. I'm just integrating a constant. And then I like to pull all the constants out whenever I can. Right? So I'm going to pull the 3 out and I'm just integrating x dx. Again, technically all of these integrals are from 0 to 1. So now what I can do is evaluate each of these integrals individually. So the integral of 1 over x I know is ln of absolute value of x. The integral of 1 is just x. And then the integral of 3 is 1/2 x squared. And what I would do at this point is evaluate all of this from 0 to 1. So I would take x equals 1, I'd plug it into all of my x variables. I would take x equals 0 and plug it into all of the variables, right, and subtract those results. All right, if I do all of that, let's see, if I plug 1 in, I get 2 ln of 1 plus 1. This is just 3/2 times 1 squared, right? So there's upper limit, and then I subtract with the lower limit plugged in. So if I take x and go, ooh, I picked a bad value of x to plug in here, right? Here's why. If I plug x equals 0 into the logarithm, ln of 0 is undefined. So let me cheat and say this is 0.5 here. 0.5 on all of these. So I was just trying to focus on the antiderivative, and I picked a bad value for my bottom limit. So I would subtract with all of that fixed. I'd have 2 times ln of 0.5, and then plus 0.5, and then minus 3/2 times 0.5 squared. Okay, and I could simplify all of that and clean all of that up, but that's not what I wanted to focus on this example. What I wanted to focus on this example was taking the original function, the original integrand that we had, 2 plus x minus 3x squared all over x, and discussing how we would find that antiderivative. Some of the homework problems, let me fix this guy too. Some of the homework problems you would see in a section like this would involve this type of technique, where we might make a mistake to do something like this on the right in green, and instead what we want to do is split up that integrand to simplify them to make them all integrals I can do individually. So again, I started with this integrand here, and I ended up with, this integrand here. I ended up with these 3 individual integrands, 3 separate integrals. So let's just take a look at a couple other examples, and I'm not even going to pick numbers like 0 to 1. I'm just going to do something like, from A to B, because I don't want to focus on that step here. So let's say I had let me say 2x minus 1 squared. So in a section like this, what I need to do in this case, well, first of all, let's just notice that that's a composition. That the outer function is the square function, and the inner function is 2x minus 1. Now, we don't know yet how to deal with a composition in terms of an antiderivative. Now, what we will do in a couple videos from now is we will learn about our first technique of integration we call the substitution rule, or U substitution. But at this point, we don't know that technique. So what we would technically need to do here is FOIL out this expression. Right? So I would need to take 2x minus 1 times 2x minus 1 and FOIL all of that out, right? So I would 4x squared minus 2x plus 1. So I'd have 4x squared minus 4x plus 1. So this expression would become 4x squared minus 4x plus 1 that I would be integrating from whatever to whatever, from A to B. And then again, technically I split all of these up, right? So I integrate 4x squared, I pull the 4 out, the integral of x squared is 1/3 x cubed. Right? So remember, I'm going to add 1 to the power and then multiply by the reciprocal. That's my power rule. I'm going to pull off the -4 here, and the integral of x, again, x to the 1 power. I'm going to add 1 to the power and multiply by the reciprocal. And then the integral of a constant is just the constant times x. And again, if I had limits of integration, I would plug in upper and then subtract, plugging in the lower value. Okay. So some of the problems in this section, again, initially won't fit one of our known antiderivatives, if you will. We'll have to do some algebraic manipulation to get to a point where I could use a power rule, or I could, recognize like integral of sine theta in that case. Let's pick another example. Let's say we had something like 2 plus x squared over, actually let me do this. Let me do 2 plus root x over x squared, let's say. Again, I'm going from A to B, but I don't want to focus on the limits of integration. Let's focus on the antiderivative here. Now, really similar to what we just did, right? The way I like to think about this is I like to split up this integrand, right? So I like to think of 2 over x squared plus root x over x squared. That's how I like to think about that integrand. 2 over x squared, I said, plus root x over x squared. Now, 2 over x squared, right, I can write as 2x to the -2 power, and then I can use the power rule by adding 1 to the exponent, multiply by its reciprocal, and we'll deal with that in a second. Now, what I need to do here is divide like bases and subtract exponents. So technically this is x to the 1/2 over x squared, and then this guy here, I'm going to divide like bases and subtract exponents. And then I can use the power rule on that as well. So, let's see, the common denominator here, I need a 2 common denominator, so I'm going to end up with 4 halves. So I have 1 minus 4, which is -3 halves. So this guy becomes x to the -3 halves, and then I have the 2x to the -2 from there. Right? So I have the integral of all of that dx. So again, just stopping for a second, right? My original integrand that we had here doesn't match. I can't do the power rule on that. Just like we talked about in the last example, I can't integrate the numerator, then integrate the denominator separately. That's not legitimate, right? And hopefully that makes sense to you, because if I had a function like f over g and I was taking its derivative, that is definitely not derivative of the numerator over the derivative of the denominator, right? This would be a quotient rule that I would do in terms of derivatives. So integrals can't be done in the same fashion. I can't just integrate numerator and integrate, oops, why did I write q? And integrate the denominator. Okay. All right, that is not true. So what we had to do in this example, right, what I boxed in red here, is we had to split up. So I wrote 2 over x squared plus root x over x. So 2 over x squared, I have to bring the x into the numerator, change the sign of the exponent, because I can integrate x to a power. Right? And then root x over x squared, again, what we did there was we divided like bases and subtracted exponents. So now I'm going to pull the 2 out and I'm going to add 1. So negative 2 plus 1 is negative 1, and I multiply by its reciprocal, right? And then add 1 to the power. So negative 3 halves plus 2 halves is negative 1 half, and then I multiply by its reciprocal. And then, you know, barring a little bit of cleanup there, you know what I just noticed? I didn't hold my parentheses properly. Right? So the 2 that I pulled out of this coefficient only multiplies this antiderivative. And I bracketed all of that stuff. So this would be negative 2 over x. So this first term, right, x to the negative 1 is really 1 over x. And then this is minus 2 over root x, technically. Right? X to the negative 1 half is 1 over x to the 1 half. Right? So, and then, you know, I would evaluate from a to b. So notice in these two examples, it's kind of illustrating that we can't integrate numerator, can't integrate denominator separately, right? We have to do some algebra cleanup there before we can actually find the antiderivative. Now we saw that same approach in our prior example. Well, actually it was 2 examples ago, wasn't it? Right. So in this example here, we had to split it up as well. Right? And then this last example we just did, we're illustrating that even notice right here, right? I have 2 things being multiplied technically. Notice what I can't do here. Let me change to green. I can't say the integral of one thing times another is the integral of the one thing times the integral of the other, right? The integral of a product is not the product of the integrals. These 2 things are not true. And again, if we think in terms of derivatives, the derivative of f times g is not the derivative of the first times the derivative of the second. There's a product rule that we would do here. We wouldn't just differentiate each and multiply. So the integrals are the same way. So for now, in this section, right, how do we get around having the integral of a product? Well, we do some algebra cleanup first. And we get ourselves to a place where we just basically have a polynomial, sums or differences of powers of x. And then when I have a quotient, you know, how do I deal with the quotient? Well, again, you know, it really depends on the specific problem we're working on. But on this example, right, we split this up, each term over the denominator, and then we did some simplification. So another type of problem you might see in a section like this, or let's say we had 2 sine of x minus e to the x, let's say, plus 1 over the square root of 1 minus x squared, something like that. And let's say we were going 0 to, let's say, 1 half. So again, we're splitting each of these up. I'm integrating 2 sine x on its own. Right? I'm integrating e to the x on its own, and I'm integrating this term on its own. And again, the reason we're doing that is because think about derivatives, right? If we had the derivative of f plus g, that is most definitely f prime plus g prime, right? The derivative of a sum is the sum of the derivatives. So the integral of a sum is the sum of the individual integrals, right? So whenever we have sums and differences of terms, we can, in essence, just integrate each term separately. So instead of writing this next step where I put the integral in front of the 2 sine, put the integral in front of the e to the x, I put the integral in front of 1 over root 1 minus x squared, I'm just going to say verbally that that's what I'm doing, and then write my antiderivative. So for this first term, 2 sine x, I'm going to pull the 2 out. And then what's the integral of sine x? That's negative cosine of x. And I'm going to pull the negative 1 coefficient out here. What's the integral of e to the x? It's e to the x. And then I'm going to integrate 1 over the root of 1 minus x squared, and that is inverse sine of x. And then I would evaluate from 0 to 0.5, let's say, 1 half. Let me leave that as 1 half, because what you're going to notice in pretty much every textbook, right, especially the Stewart textbook, we leave everything in an exact form. So if I plug all of this in, I have -2 cosine of 1/2 minus e to the 1/2, and then plus inverse sine of 1/2. So there's the upper limit plugged in, and then minus, I plug the lower limit in. So cosine of 0 is actually 1. So I really have -1 times 2. That's -2. And then when I plug 0 in here, e to the 0 is 1. So I have -1. And then inverse sine of 0. Okay, and then what kind of cleanup can I do here? Now, if I look at cosine of 1/2, this isn't something that I know an exact value of, right? If it was cosine of pi, I know the exact value of that. If it was cosine of 0, if it was cosine of pi over 2, right? Those are things I could look at, let's say, on a unit circle. I can't look up the theta value, the angle of 1/2. So what we would typically see in a solutions manual is we would just leave that as cosine of 1/2. That is its exact value. And then same thing with this guy, right? I mean, e to the 1/2 I could plug in my calculator. Just like cosine of 1/2 I could plug in my calculator. So whenever I have something to the 1/2 power, we typically convert that to a root. So again, this is some decimal, but if we're leaving things in an exact value, we're just going to leave it that way. And then what's inverse sine of 1/2? And again, think about what this says. This is saying what angle do I take the sine of to get 1/2, right? Let me write that over here. This is saying, what angle do I take the sine of to get 1/2, right? That's really what inverse sine of 1/2 is. And there is no angle, at least an exact value that we know, right? Ooh, wait a second. I think I'm wrong about that. Hang on a second. So if I have, let's see, I think if this is 30 degrees, I get 1, 2, and the square root of 3, right? Isn't that right? Sine of 30 degrees is 1/2. Yes, check that out. So 30 degrees is pi over 6. So this is really pi over 6 as an exact value. Ooh, I'm glad I caught that. So then I subtract my last term. So minus a minus is a plus 2, minus a minus is a plus 1. And then here's minus. I didn't distribute, right? And then what's the inverse sine of 0, right? What do I take the sine of to get 0? I take the sine of 0. Now, I think this is making me catch another mistake that I have, right? If I know that the sine, nope, I'm good, right? I'm thinking for a moment that this was inverse cosine of 1/2. If this was inverse cosine of 1/2, that would be 60 degrees in my triangle. But this I do not know. Do not know the cosine of 1/2. So, there's my exact value. I guess 2 plus 1 is 3. I could combine that together. But here would be an exact value in that case. All right, now, even though we took this one all the way to the end, where I did plug in my upper and lower limit, the bigger picture of what I really meant to focus on here was what I wrote over here in green, right, is that the integral of a sum is the sum of the integrals. And if you think about that, that's true for subtraction as well, right? The derivative, the difference, the derivative of a difference is the difference of the derivatives, and the integral of a difference is the difference of the integrals. My tongue is not working today. All right. So quotients and products, we have to do some algebra manipulation before we can take the antiderivative. Sums and differences, not necessary. So the next example I want to look at here, I have a classwork activity I like to give my calculus courses. And this is a problem that's on my classwork activity. And I ask my students to do some exploration with this problem to find out what is wrong with the work that you see here. So when you look at this work of this integration, it seems like everything is legitimate. Right? So if we just look at the antiderivative for a moment, the integral of 1 over x squared, I'm going to write that as x to the -2. So that I can use the power rule. And then I add 1 to the power. So -2 plus 1 is -1. Right? And I multiply by its reciprocal. So this is a correct antiderivative up to this point. And I'm evaluating, right? So I'm going to evaluate this antiderivative as x goes from -1 to 3. So I'm plugging in the upper limit. So when I plug 3 in, I get 3 to the -1, which is really 1 over 3. And when I plug -1 in, I really get, -1 to the -1, which is 1 over -1, and I get that result. Right? So it looks like this is legitimate work here. Right? Looks like we would get a numerical value. So what I ask my students to do is take out a calculator and plug this into a calculator and see what happens. So I'm bringing up my TI-84 that I have here. I think you guys can see this, right? And I'm going to do this integral. So let's say I do math, hit the math key, like we talked about before, and then I'm going to hit number 9, function integrator. So I'm going to go from -1 to 3, and I'm going to do 1 divided by x squared, and my variable of integration is x. Now when I hit enter here, I get a division by 0. So, why do I get division by 0? Well, if we think about this for a moment visually, if I think about what I'm looking for, and I'm looking for, let's say, the area under 1 over x squared. So if I graph the function 1 over x squared, it looks something like this. And we're going from, let's say, -1 to 3, roughly, something like that. So we're finding the area under 1 over x squared from -1 to 3. So in other words, we're finding the value of that shaded region and the value of that shaded region. So it looks like, right, I'm going to have infinite area. How could I have area that's a positive measurement here? Wait a second. You know what I just noticed? Don't I have a mistake in this work here? Do I? See, if I plug -1 into this expression, I have the opposite of -1 to the -1 power. So I have -1 over -1 to the +1 power. So this is -1 over -1, which is +1. Oh, that's correct. And so I'm doing upper limit minus lower limit. Okay, so that was correct. I thought I called a mistake. And the reason I thought this was wrong is it's negative area, and all this area lives above the x-axis, so it should be positive. But again, the issue here is that once I try to evaluate this integral over a discontinuity, here's a discontinuity right at x equals 0, then it doesn't matter what I get here, whether it's -4/3 or +4/3, it's just incorrect. Right? So we always want to be careful in general, right? If I'm integrating a function, from a to b, I need f of x to be continuous. I need f of x to be continuous on that interval. Okay. Now, the reality is here, and there's an exception to that statement, and in a Calculus 2 course, we'll actually explore this idea a little deeper. There actually are some scenarios where these, what look like infinite areas, aren't really infinite. They're actually finite. They converge would be the proper term. Now, in a Calc 1 course of this nature, we're not going to take that path of further exploration. We're going to say that f of x needs to be continuous. Which it does, and there's an asterisk to that. There's special considerations, special exceptions, if you will, to this statement here. But for now, this has to be true, and we'll discuss the exceptions in the Calc 2 course. We started off this whole chapter, right, this whole conversation of integration, by talking about area under a curve, and here we see area in the xy plane, but oriented in a unique manner. Typically in a homework problem within the section here, we would have what's given. The area of the region that lies to the right of the y-axis and to the left of the parabola x equals y times 5 minus y, which is the shaded area in the region. That area can be calculated as, and then here's the integral we could use to calculate that area. The integral from 0 to 5 of the function y times 5 minus y dy. So a little hint, like turn your head clockwise and think of the region as lying, below the curve and above the y-axis, right? So, technically this is the x-axis, this is the y-axis, and if we rotate this kind of 90 degrees, right, we're looking something kind of like this, right? We're looking at the area under the curve, if you will, but we're looking at the area in this orientation. Now, I don't want to get too deep here, but technically, if we think back to what we did at the beginning of the chapter, what we would have done with this scenario is we would have squeezed, rectangles under the curve, something like this, right? We would have had rectangles under the curve. So when I rotate, I see the rectangles in this manner, something like that, right? So I'd really be doing the same thing. Down here, the width of each rectangle was a delta x. Up here, the width is really a change in y, and that's where this dy expression is coming from. All right? So just to add a quick little explanation of why this integral is all in terms of the variable y. However, we're not expected to understand that. I just wanted to throw that in there real quick. And what we're being asked to do is evaluate this integral. We're being told the integral that we're given will find the area. So how would I evaluate this integral using the techniques of this section? Well, again, I have a product of things here. I can't integrate y on its own and 5 minus y on its own. I have to distribute. And that way I have this, polynomial-esque expression. I have a difference of two terms, so I can take the difference of the individual integrals. So I'll integrate 5y, and I pull the constant out, and the integral of y to the first is add 1 to the power multiplied by the reciprocal. And then I integrate y cubed, and again I'm going to get 1/3, I gave the answer, didn't I? Integrate y squared, I add 1 to 2 and then multiply by its reciprocal. And then I'm going to evaluate from 0 to 5 here. So this would actually measure the area of that shaded region in that picture we had up there. Let me scroll back up, right? This would be measuring the area of the shaded region. So to finish this problem then, I just need to plug in upper limit. So I plug 5 in. You know what I'm noticing? I keep doing this. 5 times the y is 5 times 1/2 y squared. I keep seeing brackets. So let me just fix this, right? Usually we'll just write a vertical line and then goes x equals 0 to x equals 5. Thank you guys for catching that. Somebody whispered in my ear. I appreciate that. So now I'm going to plug in upper limit minus lower limit. So I'm going to plug in the 5. So I really have 5 halves times 5 squared minus 1/3 times 5 cubed. There's plugging in the upper limit. And then I'm going to plug in the lower limit, right? Obviously 0 squared is going to be 0. 0 cubed is going to be 0. So all of that is just 0. All right, so let's see, 5 squared is 25. What is this? See, 25 times 5 is 125 halves. And then 5 cubed is 25 over 3. Then I would need to get a common denominator here. So the common denominator between 3 and 2 would be 6. So I multiplied this by 3. I need to multiply that by 3. And that is 375. And then I have to multiply this by 2 and this by 2. That was 125. Right? 5 cubed is 125. So I multiply that by 2. And what's that? That's 250. And this is 125 over 6. So I paused the video for just a second because I wanted to scroll back up to the top of our note page. So we had our exploration that we went through at the very beginning of this video. And we ended up discussing what we call the fundamental theorem of calculus. And here was one piece of the fundamental theorem of calculus. It said something like this. It said that if we have a function g of x described in terms of the integral of f, then the derivative of that function, right, was the derivative of the integral, which would just be the original integrand, was that guy, right? So what this was saying, right, through our exploration, we had noted that the derivative and the integral are inverse operations. So, we kind of mentioned that this was a little weird. This was a little weird to define a function as an integral from 0 to x, f of t dt. So for us at the moment, this integral definition of g of x does seem weird. But I want to point out to you that there are some applications, many applications actually, in the physical sciences, in chemistry, astronomy, optics, even statistics, probability, where we actually have an integral defined function. Let's take a look at a couple of those. So here's one example of an integral defined function. So if you've ever had statistics, then you've seen the normal curve. You use tables of numerical values that represent areas under the normal curve. So here's an example of an integral defined function. So the integral from negative infinity to z, where z is my variable of integration. Now, just to make things a little simpler for us mentally here, if I were to, let's say I were to choose the mu, which represents the mean of my random variable, and sigma represents the standard deviation of my random variable. If I plug in a mu of 0, and I plug in a standard deviation of 1, what I end up with here is 1 over root 2 pi, and I'll pull that out of the integral. And then I have e to the negative z squared dz. Now if I were to take out my calculator and I were to graph y equals e to the negative x squared, I'm going to see this bell curve. So again, if you take statistics and you've seen that bell curve, and let's say I'm going from minus infinity to z here. So in a simplistic form, just to get the mu and sigma out of there, right, to pick some specific values, we're integrating this expression, this integral. And this is supposed to be from z from minus infinity to z. Right? So this would calculate the area under the curve for some specific z value. And again, this isn't a statistics class. I don't want to get too deep into this here, but this would represent really a probability of observing this z value. So whenever we calculate these numerically, we create probabilities, really areas under curves. Now I do want to point out to you here that this integral we can't do. We don't have any technique of integration at this point where we can evaluate e to the negative x squared. So, we would have to use technology to do this. And if you take a statistics course, you actually have a table of values that find the area under that curve. So here's one example of having an integral defined function. We're defining a function g of x in terms of an integral. Right? It seemed pretty weird when we did that earlier. And the reason we did that earlier was to just connect to the derivative and the integral being inverse operations. But here's an example where we might actually see a function defined in terms of an integral. Another classic example here in a Calc 1 course would be to look at what we call the Fresnel function. So the Fresnel function is an integral defined function as well. We can see s of x is the integral of sine of basically x squared. Right? Let's ignore the pi over 2 for a second. We're integrating sine of t squared dt, sine of x squared dx. There is no technique of integration that we know up to this point where we could evaluate that integral. We could find the antiderivative of sine of x squared. So for now, right, in this course, our only approach really would be to estimate that integral. Now I pulled this problem out of the Stewart calculus textbook, and Stewart actually has us do something with the Fresnel integral. Let's take a look at this for a couple minutes. So this integral is named after French physicist Augustin Fresnel, and he's famous for his work in optics. This function first appeared in his publication, The Diffraction of Light Waves, and this was back around, I think, 1800. Early 1800, 1805. And it has been more recently applied to the design of highways and actually railways as well. Helps us figure out the curvature of a road as we enter a curve. Without getting too detailed here, if we think of having a straight road and then we enter a curved part of the road, right? We need this transition to be as smooth as possible, right? And what banking of the road might we need to keep us from flying off the road at any particular speed? And the Fresnel function can help us calculate that as well. Fresnel function also will look at, so if we have a light ray traveling from a source, it's going to hit and it's going to diffract to another value within inside the lens. Right? Again, I don't want to get too detailed here. But Fresnel's original work was in regards to those optics. So we have that Fresnel function. The fundamental theorem tells us how to differentiate that Fresnel function. So if we take the derivative of the Fresnel function, we know from the fundamental theorem part 1 that the derivative and the integral, undo each other. Those are inverse operations. And what we end up with is just the sine of pi over 2x squared. So that is the derivative of the Fresnel function. Now, what we're doing symbolically here is the derivative we're calling f of x. Here's our derivative of our Fresnel function. We can see in blue here is the derivative of the Fresnel function. Now, what we pose down here at the bottom of the page is at what values does the Fresnel have local maximums? Now here's a kind of zoomed out graph of the Fresnel function. So here's a local max right here, right? We're trying to find that x value. Here's another local max. We want to find that x value. Another local max. We want to find that x value. Now, if we notice, right, what we're doing, here's the Fresnel function. Right, in red, the Fresnel function, we're wanting to find the max values. Here's its derivative in blue. Right, remember, wherever the derivative equals 0, there's a max on my function. Right, wherever the derivative equals 0, right, we have a minimum here. Right, whenever the derivative equals 0, right, we have another max on my function. So what this problem out of Stewart's textbook is asking us to do is find those max and min values of the Fresnel function. Find these values of x for the Fresnel function. Right? Now again, remember, whenever we're finding max or min values for any function, we take the derivative and we set it equal to 0. So if we're finding the max or min values of the Fresnel function, we're taking its derivative. So again, here's the derivative of the Fresnel function, and it's this guy right here, sine of pi over 2x squared. So I need to set this derivative equal to 0. So I'm going to take sine of pi over 2 x squared and set it equal to 0. Right? That's the derivative of the Fresnel function, setting it equal to 0. So when does the sine equal 0? So if I think of, let me write it this way. Let's say I have sine of u equal to 0. Right? When will sine be 0? Well, whenever the inside is some integer multiple of pi. Right? So if we think of sine of pi, or sine of 2 pi, or sine of 3 pi, or so on and so forth. So whenever the inside of the sine function is an integer multiple of pi, then the derivative will be equal to 0. So, I would have pi over 2x squared would have to be equal to pi, or I would have pi over 2x squared equaling 2 pi, or pi over 2x squared equaling 3 pi, so on and so forth. So if I take this first one and solve for x, I'm going to multiply the left by 2 over pi, and I'm going to multiply the right hand side by 2 over pi, and I'm going to get just 2. So I get the square root of 2 as the first maximum value. Now you can't see, I scrolled away here. Let me scroll back up. But right here, there's my first maximum value is, square root of 2. What are you doing? Go away. All right, and then, if I were to continue this, right, let's say I have this second guy, pi over 2x squared equals 2 pi. So to isolate the x squared, I'm going to multiply the left-hand side by 2 over pi. I'm going to multiply this by 2 over pi, and it's going to give me 4. So that's the square root of 4, which is technically 2. And then over here, I multiply by 2 over pi. I get x squared. I multiply 3 pi by 2 over pi, and I get 6. So I get the square root of 6. You can see a little pattern here. Root 2, root 4, root 6. I'm going to have root 8 and root 10 and so on and so forth. Now if we come back and look at our graph real quick, we can see that root 2 is going to be this first guy. Root 4 is going to be that guy as the minimum, right? Root 6 is the max. Root 8 is the min. Root 10, root 12, root 14, so on and so forth. So root 2, root 6, root 10, root 14, those are going to be all of my maximum values in particular. Okay, so I think I've spent a long time here in this section. This last example is just kind of a cool example to show you where an integral defined function might actually be seen in the real world. In summary, in this section, what we really have looked at is the fundamental theorem of calculus. Fundamental theorem of calculus tells us that a derivative and an integral undo each other. That really tells us that when I evaluate an integral, I'm going to do an antiderivative. So let me scroll back up here, right, just like we kind of saw in this last example. So when I evaluate an integral like y times 5 minus y, I'm going to find the antiderivative of 5y minus y squared. So here's my antiderivative, and then I plug in upper limit minus lower limit. So that really was the end result of this section. We ended up having a shortcut for finding, for evaluating an integral. So in the prior two videos, 5.1 and 5.2, we evaluated integrals by using approximating rectangles to estimate area under the curve. And what we do here in 5.3 is we create a shortcut. We did that exploration on the first couple pages to conclude, right, to explore and discover that the integral and derivative undo each other, which really defines an antiderivative that comes out of the integral. All right, I will see you in the next video.